Thanks for joining. This is the series on the internals of the NEAR protocol, and we're going to be focused mostly on the runtime this time. Runtime in NEAR protocol is quite complex, and to understand why certain things are done this way in the runtime, we need to understand the motivation about it. Motivation behind the NEAR runtime is that we want to have a very good developer experience for people writing contracts in NEAR runtime. And what it means is that we don't want them to think that they're running on the blockchain too much or that our blockchain is sharded. We don't want to expose the internals of our blockchain. We want them to just write code with Rust or assembly script or whatever, and using the primitives that they're familiar with, like promises from JavaScript or futures from Rust, and don't think exactly how it's going to be executed. What it means for us as the developers of the blockchain is that we want to hide the complexity that we would otherwise expose to developers inside the blockchain protocol. And the place that it hides all this complexity is called the runtime, or more specifically, transaction runtime. So transaction runtime is this black box that has lots of logic about how to process transactions and how to execute the contracts in such a way that it looks very friendly to the contract developers. This is going to be a series of videos about the transaction runtime because this topic is very complex. It's going to take quite some time to explore it. The video today is going to be mostly about the overview of the transaction runtime. And so we're not going to dive into the details of exactly how WebAssembly is executed or anything like that. So let me start first by sharing with you like a little bit of drawing that I'm going to make. There we go. So NEAR blockchain is sharded, which means we have a bunch of shards executing stuff in parallel. In the NEAR blockchain, both execution and state is sharded. Some blockchains, they don't shard state, but in NEAR, we shard both execution and state, which allows to not have huge disks for the nodes if they choose to follow only one shard on NEAR blockchain. Each of the shards has its own runtime. I'm going to put a rectangle like this. And each of these runtimes executes in parallel. So that's the thing that is common to many blockchains that are sharded, is that there is a lot of parallel execution happening. And because execution is parallel, that means that this abstraction is gonna spill over into the contract execution. So the contracts will be doing asynchronous cross-contract calls in some cases, as opposed to synchronous contract calls that are typical to Ethereum blockchain, because Ethereum blockchain is not sharded. But we're not going to dive into the details of why, what is a synchronous contract call is from the perspective of the contract developer. What you need to take from here is that there are multiple runtimes running on NEAR blockchain, one runtime per shard, and these runtimes execute in parallel. And you can think of each runtime as a state machine. And now I'm gonna show you more or less what is the input and output of the state machine. Gonna use CLion, which is our typical development tool for the code of our blockchain. So the code that you want to start looking into, if you want to familiarize with our runtime, lives in the runtime folder under runtypes subfolder. And the most of the high-level things that you need to know of, they live in lib.rs. So in lib.rs, we have this class called struct called runtime, which in this case you see it's stateless, and it's kind of.
Hey Max, can you please increase the font size a little bit?
Yep.
Thanks.
Oops, how do I increase the font size? Maybe I can decrease this size like this. Is it better?
Seems like, yeah.
Cool. Right, decrease the size of the window. So this is a bit janky here, so don't put too much attention to it. What we actually should have had here is we shouldn't have had struct runtime, because it's stateless. There's nothing inside, and we should have removed all this references self from these methods, because self is not actually used here. I mean, there is no state in self. So this is just FYI. This is the code that needs to be refactored. But things that you're looking at the runtime are basically two functions, apply and apply genesis. Can you see them in this pop-up window that I'm presenting to you? Cool. So apply function, here it is, I navigated to it. That's basically where you're gonna get like 60% of your knowledge about the runtime. Just by looking at the signature of this function, like you can meditate on it, take a nap, and think about it like tomorrow, what the signature of this function is. But this is where like 60% of the knowledge of what runtime is doing is actually concentrated in the signature. The signature represents the state machine of the runtime, what it takes as an input and what it spits out as the output. And additionally, you can think of it as there is input, there is output, but you can think that there is a state. And so, you know, when the runtime executes something, it also updates the state. So as I said, the runtime is a state machine. And one step of the state machine of the runtime is execution of the one block, or because our blockchain is sharded, execution of one chunk. So if you don't know, chunk is basically a struct that contains the transactions and the state on a specific shard, and chunks are aggregated together into the block across all shards. So one step of the NEAR runtime executes one chunk on that shard, and the two main inputs into the state machine are the receipts and transactions. And what it spits out in the apply result, if we go there, are more receipts and some other data that I will also go over. But basically more receipts and some information of what is the execution result of this thing. You see here also there are some fields about the state. We're gonna touch it later. And some stats, some proofs. This is all useful, but not as critical for the runtime execution. Most of the important stuff is in outgoing receipts and outcomes right now. That's what you need to focus on. So what are the receipts? Let me go back to the NEAR blockchain. You have transactions and receipts as two main primitives that runtime operates with. Receipts is basically a message that's been sent between shards, right? We don't want shards to work in complete isolation, because if they were working in complete isolation, that there wouldn't be any use of having a sharded blockchain. That would be just like a bunch of separate blockchains. So the shards need to communicate with each other. And the way they communicate with each other is using the receipts. So receipt is basically a message that shards exchange with each other, or they exchange with themselves by just like, you know, saving it somewhere and then processing it later. So think of a receipt as having exactly the same body as a transaction minus signature. So receipt is basically a transaction that passed the validation that yes, this is the account that issued this transaction, stripped of the signature, some of the fees were paid, like almost exactly the same information as the transaction. So what flying in between the shards are the receipts. So when they execute, when one shard executes one step of the runtime, it consumes transactions, a batch of transactions and receipts, and it spits out a bunch of receipts. So that's what comes in, but what comes out is a bunch of receipts. Some of these receipts, they now fly to another shard on the next step. Some of them, they circle back and being reprocessed by the same shard on the next step. And that's essentially the high-level step of the state machine of the runtime. It takes transactions and the receipts and spits out the receipts. So the question is where transactions are coming from. Transactions are coming from the RPC. So that's the RPC server of the blockchain node, accepting the transactions from its users. Well, more specifically, first it's the RPC, then it gets into the transaction pool, but you got the idea. Basically, the users provide the transactions once they go through the transaction pool, put into the chunk, they end up with the runtime. And runtime consumes transaction receipts and spits out more of the receipts. All right. Now let's go back to the code and look at the body of the receipts and transactions. 1 second. So here, as I said, this is where most of your focus should be if you're trying to understand the runtime, the apply method of the runtime structure. And two important fields here are incoming receipts and transactions. So incoming receipts are what I just said. Those are the receipts incoming from the other shards. Some other shard wants us to process this on some shard, A wants to process it on shard B. That's how they relay the receipt, and that's where it gets into the runtime. And here's the signed transaction. So let's look at the signed transactions. Signed transaction has, as I said, the signature, the hash. The hash is computed on the fly. It's not actually serialized and passed through the network. It's computed upon the deserialization of the transaction. And then there is the transaction body itself. The transaction body has some information on like who signed it, what is the public key, what is the nonce, like who is receiving this transaction, and a bunch of actions. So if we look, for instance, in the receipt, let me get receipt. Oops, sorry. In the receipt here, if you go all the way deep into the action receipt, and I'm gonna talk later what action receipt versus data receipt, you also see that there's a bunch of actions in there. So this is basically the body of the receipt, the list of the actions, and the body of the transaction, also the list of the actions. All other information is kind of auxiliary. The signer ID, again, output data receivers, we're gonna go through all that, but most of the stuff is inside the actions, both for the receipt and the transaction. And what is the action? It's actually what we want to do. Do we want to create an account with this transaction or this receipt? Do we want to make a function call, transfer some NEAR tokens, stake, we give a proof of stake, blockchain, delete a key, add a key, and delete an account. So these are the actual things that we're gonna execute on our blockchain. They're stored inside the action. And the reason why we have a list of actions, both in the transaction and the receipt, is because unlike many other blockchains, our transactions are batched, meaning if you want to do multiple things, in NEAR, you don't need to execute multiple transactions. If I want to create an account, deploy a contract, add access key, call some function, I don't need to execute to submit a bunch of signed transactions in a row and somehow make sure that they all execute in the right order. In NEAR, you can bundle them.
I have a question. Is the execution of a single action receipt or transactions atomic? So is execution of entire receipt atomic or only individual actions?
Yeah, the execution of the entire receipt is atomic. So if one of the action fails, then the whole receipt is unrolled, or rolled back, sorry. And this is useful when you want to issue a very typical batch transaction, which is create account, deploy a contract, call an initialize method on this contract, add an access key. This is like, 4 very typical actions that you will frequently want to bundle together. And what we don't want to happen is that we create an account, deploy the contract, but our initialization function failed. And so we have this contract hanging in the air without even access key being added to it. So no one can do anything with it. And to avoid this, the entire set of actions is getting rolled back. So the entire receipt is atomic.
Does it mean that the actions, they are performed in the same order that they are in this vector?
Yes, it's important for them to be performed in the same order. And there are also even some crazy things that you can do with these actions. For instance, you can create an account, deploy a contract, call a method on it, delete this account because you don't need it anymore, maybe, I don't know. And then create another account. No, I mean, you cannot create another account currently, but you get the idea. You can do this kind of crazy stuff right now. And that's the point. There are some restricted sequences that you cannot do with this. for certain reasons, because we either didn't implement it yet because it would be hard to implement. For instance, creating two different accounts in the same receipt. You cannot do it right now. You can only create one account. You cannot do multiple times create delete back and forth because that would make us grindable, because deletion of the contract is very expensive, just like on Ethereum. Ethereum also has issue with this. And it's actually one of the economic vulnerabilities of Ethereum, deleting a very large contract with a very large state. So in our case, for instance, that would be a prohibited sequence if you try to create, delete multiple times an account in the same receipt. Right. Any other questions?
Does the receipt has a single destination account? I don't see in the structure the information. So I think it should have destination account, yes, and also predecessor like sender, yes, account, possibly different from signer.
Yeah. So destination and sender are here. So again, I said that the auxiliary information of the receipt and transactions differs slightly, right? So in case of the receipt, you have a fixed receiver ID. You see, it even leaves several levels above the actions, right? It doesn't leave even a receipt and up. It doesn't leave an action receipt. It leaves all the way up. Here's the receiver ID. Who is receiving this receipt? And receiver ID also identifies what would be the name of the account that you're creating. So when you're creating an account, your action is going to be create account, and your receiver ID is going to determine what is the name of the account that you're creating. That's why when you go all the way into the actions and you look at what is the create account action, there's nothing in here. Like, it's empty. It doesn't say what account you want to create because the account name has been determined from the receiver ID. And in terms of the signer and sender, so for the receipts, we're still gonna dive into detail later what it means, what predecessor ID is. In case of the transaction, let's go into the transactions. Send transaction.
Can I ask a short question about, yes, the receipts? About the actions. Mm-hmm. So Max, you said that there is no synchronous calls inside of NEAR blockchain. So there are no composability of smart contracts like in Ethereum. But can it be changed with the fact that all the actions are going to be implemented atomically here? So like for example, if you apply this to DeFi, you're buying here some tokens, then you're putting this to the to some kind of pool, and then you're like calling some lending contracts and stuff like that. Can you do all of this in this set of actions?
Yeah, so the reason why the classic composability breaks is because the classic Ethereum composability allows you to do atomic on multiple contracts at the same time. The thing about NEAR is that these contracts can live on different shards. And so you cannot create atomic operation yet. I'm not going to spoil anything. Not yet. Maybe in the future, who knows? But right now you cannot have an atomic operation that spans two contracts that live on different shards, because they don't live on different shards. It's asynchronous. And batch transaction, batch receipt that we just looked into, is being executed as a batch on a single shard. So this batch is executed only on one contract on a single shard. You cannot have a batch across two different shards.
But can you apply this to different contracts on a single shard?
Technically, we could have actually allowed it, but the way we designed the runtime, and this is like a really great segue question to how the reasons why our runtime is designed like that, is we didn't want to create any incentives for the people to try to collocate their contracts on the same shard with someone else. Because when you have these incentives, it's going to create very perverse system. People will try to collocate with exchanges. They will try to, certain shards are going to bloat for some reason. And the situation right now is that there is like literally no reason for someone to try to host their contract with some other contract on the same shard, because because the way it works, and let's go back to this diagram that I showed. Right, okay, presenting the correct window this time. Is that, for instance, if I'm on this shard A, right, and I'm calling from contract Alice and contract Bob, if contract Bob lives, let's say, actually in here, what is going to happen is that Alice contract will emit the receipt that was going to fly to the shard with Bob contract, and that's where it's going to be executed. So it's going to be executed one step later, right? We still have blocks in our blockchain. So in block X, Alice is going to be executed. In block X plus 1, Bob is going to be executed. And the way it's going to be executed is it's shard with Bob contract is going to receive the receipt that says, please call Bob. If Bob was living actually not on this shard, but on the same shard with Alice, what would happen is that the receipt would still fly, but to the same shard. And so it would be executed exactly the same way as if Bob was living on a different shard. And that creates like a fair system where there is no reason for you to try to put Bob on the same shard with Alice. I don't know, cut the latency or somehow create some kind of atomic execution or anything like that. And this is kind of important for us because we don't want to think about this additional adversarial vector where people are trying to jam things on the same shard. This creates a new level of complexity if you try to think of, right, now we have to protect from people trying to put things on the same shard. You have a new game theoretic model in there. You have different attack vectors that you didn't even think before. So we simplified this thing and said, okay, there is no reason for people to collocate on the same shard. And also we were thinking, and we're still thinking about dynamic resharding, right? We're thinking that our shards are going to be dynamically repartitioned in the future. So if one shard accidentally bloats, we need to cut it into pieces, and repartition it. And if people try to game this system, try to work against the dynamic resharding when they've been, put on a separate shard, and then they try to go back to the original shard again, then it's going to be just a nasty game with our protocol. Again, we don't want to think about it. So this whole concept of removing incentives for people to collocate simplifies the protocol design like drastically.
Right. Is shard A directly sending it to shard B, or is there some sort of coordinator?
The coordination is kind of implied. So it's a completely different topic of how actually receipts are related between the shards. There is no additional actor existing here. All of the actors in our blockchain are validator nodes that accept the chunks. Again, the chunk is the piece of the block specific to the shard, and they are emitting those receipts. They're exchanging them with each other in a certain way that allows to ensure that those receipts are actually received. But there is no like additional actor in the play who is takes the receipts and puts it into the other shard. Okay. There is some mechanism of broadcasting that allows to do it pretty securely with certain guarantees. Yeah, but it's a different topic which goes into the direction of our consensus and how blocks are produced and how synchronization between different shards is happening. All right, so going back to the runtime. So with the transaction, going back to the question of where is the originator? In case of the transaction, the originator is the signer. So whoever signs the transaction is considered to be the originator of this transaction, because we use the assets on the account of the signer to pay for the initial fees. Every operation on a blockchain should cost something in tokens, because it incurs certain computational costs to the validators that process these transactions. And so every time you convert a transaction to the receipt, you actually causing some validators some CPU cycles. And we have a fee for this. We have a fee that says, what is the fee of converting transaction to the receipt, actually? And sending transaction, and sending the produced receipt across the network, or and processing it on the other end once you receive it. And therefore, when transaction is being received the first time, the first thing we do is we deduct the assets we deduct the assets from the account that signed it, and we convert this transaction to the receipt. That's like the very short life cycle of the transaction. As soon as it enters the runtime, it becomes a receipt. Let's look at it. Let's look at the supply function that I said is like the core of the entire runtime, and just trace what happens to the transactions here. Transactions. So you see, we iterate all the transactions in this method. We take these transactions, and what we're doing, we're producing receipts out of them. So you see, there's a method called process transactions, but what it spits out a receipt. So this method, what it basically does, it takes transaction, gives a receipt, exactly the same set of actions stripped out of the signature, because the receipt is basically a trusted transaction, right? When we exchange the receipts between the shards, we know that we can trust its receipts, because originally these receipts were transactions, so we already verified their signatures. And we also verified that the amount of gas that was attached to this receipt is also something that the transaction signer can pay, because we actually have deducted it from the account. So yeah, that's a very short cycle, life cycle of the transaction inside the runtime. It becomes a receipt quite quickly. And it can fail to become a receipt. If, for instance, the person who signed the transaction, the account did not exist, or they didn't have enough assets. Actually, if the account did not exist, it might actually be filtered out even before it enters the runtime. So one thing to know about the runtime code in general is that the specifics of the runtime code that makes it very different from other code in our NEAR core is that it's pretty much...
Max, can I ask a question?
Yeah.
So at the moment when the transaction is converted into the receipt, you need to know the amount of money or the amount of tokens stored on the creator, on the sender of the transaction. Yes. So does this information needs to be synchronous in between all of the shards? Because
the state is sharded.
Yeah, the state is sharded. Yeah, so if the account lives on the shard A, and the account creator is sending a transaction to the shard B, how the shard B would understand whether it is enough tokens on the account?
Great question. Shard B doesn't need to know. So what happens? Let's walk around the scenario. Alice signs a transaction and sends it to shard A, where A is like Alice. That's where her contract lives, or like your account lives. When the transaction is signed, Alice needs to specify how much gas needs to be attached for all kind of operations in this transaction. Right? It's very similar to what Ethereum has, but in Ethereum you have max gas limit. So you're kind of specifying the maximum amount of gas that you're going to use. In our case, you're just saying that it's not the max gas limit, it's actually what I'm going to attach to my transaction. So when the transaction here is being converted to the receipt, what we're literally going to do, I think somewhere here, is actually we're going to deduct from the balance of Alice the necessary amount of tokens to pay for the gas that is going to be attached to this transaction. Let's look at it somewhere here. Verifying charge transaction. It's pretty straightforward. The method tells you what it's actually doing. It verifies transaction and charges for it. It charges
but who
Alice.
Is doing this? Who is doing this?
The shard that hosts the Alice's account executes the runtime. Okay. This is the runtime that we're looking into. This runtime.
But this means that this shard. Yeah. Okay. Okay. Yeah, I got it. But what about the transactions that Alice sends to the shard B?
Yes.
Because she wants to to work with the contract that was deployed by Bob.
So when Alice, let's say, wants to call, I mean, that's a great question, right? It's a bit of a different scenario, but it's actually pretty similar. So what the previous scenario that we examined was Alice has a contract on shard A, and Alice's contract wants to call Bob's contract on shard B. Assume that Alice doesn't have a contract, and Alice just wants to call contract Bob here. For that, Alice needs to have an account, because you need to, in order to execute anything on the blockchain, you need to have an account. So suppose Alice's account lives in here. Alice creates a transaction that calls contract Bob and uses the signature from her own account. And she knows that there are enough assets on the Alice's account. She sends this transaction to the RPC. Node receives it, and Node knows that Alice's account lives on shard A. So this transaction is going to be routed to the account, to the shard that hosts the account that signed the transaction, even though the contract that we are calling first is on shard B. So shard A that hosts Alice's account will do all this deduction, and that's all it's going to do. It's gonna convert transaction to the receipt and spit out the receipt, and the receipt is going to fly to Bob's shard here. And with some gas attached. So on shard A, we have deducted from Alice's tokens certain amount of tokens to pay for the gas that we're going to attach. And now this gas is attached with the receipt and it's flying to Bob's to shard B with Bob's contract. And shard B doesn't need to verify that yes, Alice indeed has this amount of tokens because receipt says so. Receipt says that don't worry, we have already deducted all this gas from somewhere, and this is the amount of gas that you can use for your own execution. And when Bob's contract is done executing it, it's gonna send a refund back to Alice's to the Alice's shard. It happens automatically. The user doesn't need to do it. So some amount of gas is not going to be used, and the remaining gas that wasn't used is going to fly back to Alice's to shard A with Alice's account and gonna be attached back to Alice's account balance, converted back from gas to NEAR tokens, using the same price that was initially used to convert tokens to gas.
But does it mean this receipt with gas attached is signed by validator A, so that's how validator B knows that it's valid? Or?
Yeah. So receipts are produced as receipts are artifacts of executing transactions, right? Just like the state. For instance, in Ethereum, like when you execute a transaction, the input are the batch of transaction. The artifact is the new state root or the new state try, right? One of the artifacts in our chunk execution is a batch of the receipts. Not only we give you new state on the shard, but we also say here's the set of the receipts that you need to execute on other shards. And just like with the state root, you trust it because validator signed this block, this chunk. Validator said, this is the chunk I executed, this is a new state root, this is the new set of the receipts that you need to execute on other shards. So it has the same kind of level of security as the new state root. And therefore the receipts, as I said at the beginning, unlike transactions, they don't have signature. They're stripped of the signature. You just trust them because the only thing that you can produce the receipt is the validator when they process in a block. User cannot submit receipt from the outside. User can only submit transaction. So you trust, if the receipt says certain gas was attached, you trust it because some validator computed it and deducted this amount of gas from someone's balance. So this money are coming from somewhere.
Okay.
Cool. All right. So this whole dynamic, so like how refunds work and like the receipts, it's quite complex, and we can like go for multiple scenarios. Maybe in the future. I think like the best way to understand runtime once you understand the signature of the supply method is by reading the apply method. So the specifics of the runtime code, oops. So the specific code of the runtime code is that is different from the rest of the code in the NEAR core, is that it's spec for the implementation, which is also kind of embarrassing that we have spec defined by the implementation. So if we were to write a spec of the runtime, which we're trying to do for quite a long time right now, you would actually go over our code and reverse engineer what is the spec, like what are the rules, like what are the rules? Like, do you execute transactions first before the receipts, or you first execute the receipts that are coming from the other shard? So all these rules are basically defined by how code is written here, which means the cost of accidentally switching two lines of code that are actually two lines of code that correspond to the spec rather to the implementation is quite high, right? Here is a more specific example. Like when you read the apply code, the code of the apply method, and let's skip all these things. We like, yes, something is happening to the state, some initialization. We converted the transactions to the receipts. We processed something like called delayed receipts, I think, local receipts. So we're processing local receipts, then we're processing incoming receipts, and then we're checking the balance. The order of operation is extremely important here. I'm processing the proposals here. This is basically the spec. If we were to write the spec of the runtime in pseudocode, we would have said, iterate over the transactions, convert them to the receipts using the following algorithm. Then take something that is called local receipts that I haven't explained yet and do something with them. Then process incoming receipts. Then check the balance at the end. The order of operation is extremely important here. And if you accidentally working with the runtime code and you switch something that is actually correspond to the spec rather than implementation, then you might actually break the protocol. For instance, I can switch these lines together and nothing actually is going to happen. It's quite obvious. In initialization functions, they don't do anything, right? It's not a spec. But if I, for instance, replace the signed transaction and with local receipts first, then I might break the spec. So this is the big nuance of working with the runtime code, is that you gotta thread carefully. Something can be the spec, something can be implementation. And if you modify it, you need to know which one is which. And the only way to know which one is which is to get this kind of knowledge transfer that we are doing right now, and to actually learn what is spec and what is implementation. All right. So let's just walk through this apply function step by step, and I'm gonna explain to you on high level what is happening here. So
I have a question.
Yeah, go ahead.
So in Ethereum, there is a step when some validation is done for transaction, if it's failed, that this transaction cannot be included in a block at all. Like, for example, if the account doesn't exist or it doesn't have enough balance to prepay for gas, then this transaction cannot be included in a block. And if someone includes it in a block, that this block is completely rejected. So what do we have in NEAR? Like, which transaction cannot be included in a block at all?
Yeah, so we have several steps of filtering transactions and balancing them early on. Some of them that happen before the transaction enters the mempool. Some of them happen when transaction exits the mempool.
I have a question regarding blocks. So if some validators possibly running changed code which disables some filters, is a block which includes an invalid transaction, like a transaction for which signer account doesn't exist, or signature not valid, or no, like zero balance at all, or low balance, what happens?
Yeah. So this is something that I don't know from the top of my head, right? I don't know whether this is something that we determine as an error, or like as a malicious behavior, like this should not be happening, like protocol violation. Is this the protocol violation, or is it just the implementation detail of the validator node? And the way I can answer to your question right now is that I'm gonna look into this runtime error. So as I said, this apply method and its signature is like extremely important. I know that all of the errors that can happen when runtime processes the block or the chunk are going to be in here in this runtime error. So I'm going to look into it, and I'm going to try to find something that going to tell me that something is some error that says that the block wasn't correctly composed. And what I'm looking into, the storage error, I don't think that it's here. Balance mismatch. This is going to explain you later what it corresponds to. Validator error. Epoch manager, this is not it. So this is about how we distribute the rewards between the validators. And receipt validation error. And here you can see certain things is that we're gonna spit out an error if you don't have the signer ID. Like for instance, someone tried to create a chunk with transactions that just don't have signer like that. Then we're gonna spit out the error. So at least partially the answer to your question is yes, we're gonna have runtime barfing out an error if, for instance, someone tried to give it a chunk with the transactions signed by non-existent account, even if it happens after the mempool.
But
same with
is
receiver
this
ID.
validation performed, like, for example, I know that if a block that a chunk, it doesn't that the state that is included in the chunk is before applying any transactions in that chunk. So it might be possible that transactions are not valid, like for example, transactions specify signer account ID and then the account with that account ID doesn't exist at all. So when will it will be detected that this transaction cannot be valid for that state?
Yeah, so as I said, like it definitely is going to be detected when runtime will try to process this, but I think there are checks. Like I know there are checks before the transaction.
Will that block be rejected that includes this such new transaction?
I think it will be rejected because you see this error. This error is global for the block, right? As I said, the apply method acts on the entire block, right, an entire chunk, and it returns you only. It doesn't return you a vector of errors. It returns you one error. So this error that says that signer ID is invalid, it corresponds to the entire chunk. So it basically says in the chunk there is a receipt with invalid signer ID. So that means from that I deduce, by reading this code, is that the block is going to be rejected because otherwise, why would you return an error like this for the entire chunk? Yeah, so that's like the value of reading this error messages in the signature of the apply method, that it kind of provides you with this information. Yeah. So going back to the apply method body. So what you see here, something about the state. State is probably going to be a separate video of how exactly we modify the state when we process the blocks. So I'm gonna skip it. Just ignore this. Nothing is happening here. Move along. Then validator account updates. So what are the validator accounts? These are basically the entities that produce the chunks in our system. And they need to be rewarded for doing that. It's a proof of stake system. The rewards needs to flow to them proportionally to how much they participated in it. So there is something is happening on each chunk in terms of like how we maintain these validator accounts. And we don't need to go right now deep into this. It's going to be a separate probably video about how we actually manage validator accounts, how we distribute the rewards, what is the cadence there, what are the rules of distributing the rewards and updating the validator accounts. Now there's a bunch of initializations. Let's not go through them. Let's actually go through the code here. So this is something I have explained to you already. The first thing we do, we take the transactions that are meant to be processed in this block, and we convert all of them into the receipts. Each one transaction means one receipt. And here you see a very interesting thing happening here. So this was actually added at some point later. This is not necessary. This is kind of an optimization of usability of our runtime. Depending on whether transaction has the same signer as the receiver, we do something different in here. So what exactly do we do different? We do a small optimization, which says if Alice, for instance, calls, let's say, its own contract living on its own account, right? Alice calls itself, then we don't need to produce the receipt that would fly and let's say to a different shard or be processed on the next step. We tried to actually process it right away, and that's what is called the local receipt. Local receipt is a receipt that's been tried to process right away. And given this whole, conversation that I gave you about how we don't want to incentivize people to collocate on the same shard, this actually doesn't create any kind of perverse incentives. This is like the only exception when we're gonna do something specific when stuff is being executed on the same shard. It only applies to the situation when the transaction is for the function call that calls itself. That just allows people to wait, in most of the cases, 50% shorter when they do the contract call on the NEAR blockchain, because most of the contract calls on the NEAR blockchain is just a single contract call. There is no cross-shard invocation. And instead of waiting for like 2 blocks, they're going to wait for 1 block here to be finalized. So it's just an optimization here. So again, local receipt is the result of transaction calling an account which is the same as the account that signed this transaction. And it's just an optimization of usability. Everything else is an outgoing receipts. Also, you can see we're keeping a count of how much gas was burned, and this is going to be important later. And we are like recording the outcomes. So outcome, it's basically our way to record the result of performing certain action. In this case, converting transaction into the receipt. So converting transaction into the receipt might produce certain errors. And people who do this on NEAR blockchain, they want to see them in RPC. They want to see, for instance, that they tried to sign with an invalid public key or stuff like that. So that would produce an outcome that will be displayed eventually in one of our interfaces. Then let's keep this. This is also like implementation details here. This is Lambda. Also, we don't need to look into what is inside the Lambda. Let's look at these large cycles. So basically, the second point of focus that you want to have while reading the apply method code is those large cycles. Like when you're iterating over the transactions, or you're iterating over the local receipts, or you're iterating over the, this is like not for cycle, but it's also important, or you're iterating over the incoming receipts. So let's just focus on these cycles right now because we have only a few minutes left. So the next thing, as I said, is right after you convert a transaction to the receipts, you're going to try to process the receipts that are local, receipts that correspond to the transactions that call the contract or the account on the same shard. So that's what you do. You iterate over the local receipts and you call the method process the receipt. We can revisit it next time. And at the same time, what you're doing, one second. At the same time, what you're doing is while you're doing all that, you're keeping track of, am I outside the gas limit? Because we have a limit for the gas in our chunks. So while you're doing all that, you're keeping track of the total gas limit. And if you did exceed the gas limit, then instead of processing this receipt and executing the function call or creating an account, what you're doing is now you make it a delayed receipt. So the delayed receipt is a very interesting concept, which is allows us to not drop the receipts. So in our blockchain, it's very, very important to not drop the receipts and always execute them. Once receipt is produced by converting transaction to the receipt or by doing a cross-contract call, it should be processed, because this is the guarantee that you need to have if you want to build any kind of DeFi on NEAR blockchain. If you don't have guarantee that the receipt is going to be eventually executed, you cannot have any kind of like locking unlocking scenario. You cannot you cannot even like exchange tokens on exchanges. So this is like a fundamental guarantee of NEAR blockchain, is that the receipts are going to be eventually executed. And that's why when we're out of the gas for this block, instead of just dropping this receipt, we're putting it into delayed QA. And this delayed QA, it lives inside our state. So the trie, the Merkle-Patrizia trie that in Ethereum just contains the state, in our case also saves what is the current queue of the receipts that we haven't processed because we ran out of gas limit on the previous block. This is the difference between, let's say, Ethereum and us, that we have delayed receipts queue that lives in each single shard. And so what we're doing here with delayed receipts, we're trying to process them. So once we went through the local receipts, And now we're gonna process them. So somewhere here we have process receipt things. I forgot, where is it?
Max, does it mean that the fresh transactions, they end up in the local receipts, and only then we are processing the delayed receipts? So this is like last come, first served.
Yeah, so the local receipts have a priority over the delayed receipts. You try to process things that are local, then you try to process delayed receipts. I think then you try to process incoming receipts. So somewhere here you process delayed receipts. I don't remember where. Wait, delayed receipts. So delayed receipt indexes, next available index. So yeah, you iterating over the. So basically, this function, what it does, it pops the delayed receipts from this QA that lives in the state and processes it. Yeah, here's process receipt. So you're extracting it here from the state. You literally, here you can kind of see that you go into the state and you say, okay, what else haven't we processed yet? What is the delayed? You extract the receipt from the state, from the Merkle-Patch reset try, and then you increment this index that says the queue has moved, and then you process this delayed receipt. So then after you're done with the delayed receipts, you process incoming receipts. So you first take care of the receipts of your own receipts. You're the shard. You care about your own stuff. You care about your own local receipts. You care about your own delayed receipts. Only after you're done with all that, then you start processing the incoming receipts from other shards. So incoming receipts are the receipts that you received from other shards on the previous step, and you also process them. And that's it. That's basically what this apply method does. So again, just to go over these major steps. It converts transactions to the receipts. It processes local receipts. It processes delayed receipts. It processes incoming receipts, like four major things that it does, in addition, of course, to doing some work for updating validator information. And finally, the last important thing that you see here is this check balance. So this check balance is an extremely important method that we have that prevented a whole bunch of bugs in our system. And what it does, it makes sure that money are not coming from nowhere and they're not disappearing into nowhere when the chunk is produced. So it's basically an assertion. It's just like this is basically an assertion living here. It's a very, very large and heavy an assertion that
Post-condition invariant.
Yeah, it's invariant. Make sure that invariant holds. It goes over this different manipulations with the balances that we had, all this gas that was, converted from tokens, tokens converted from gas, even validator rewards distributed, gas burned. Sometimes it can be accidentally burned. And it makes sure it just adds up. Like it just makes sure that, these two variables, what should be and what shouldn't, that this invariant actually holds. Otherwise, you're going to have balance mismatch error and your node is going to panic because it's a broken invariant.
When did you last see a balance mismatch error?
What?
How long ago did you see a balance mismatch error the previous time?
I mean, we only saw it in the CI, I think, because we have a pretty good nightly with this NADAC and all that. So it only happened, I think, when we just forgot something, like some specific corner case, and it was caught. So yeah, it only happened when we were actually merging things, not in production. I don't think it happened in production. Yeah, so that's it. I think that's a good high-level overview of the apply method. And if you focus on this, on the signature again of the apply method, on the signature, try to understand what gets in, what gets out, on these four major cycles that I gave you overview of, you will already have like 60% of understanding of the runtime that you might need if you're working with the runtime code. Like if, for instance, if you're working with EVM or with RPC, or like you build and bridge, things like that. So that's it. Does anyone have any questions?
I have a question. So as far as I see from the code, we are not counting for moving transactions into receipts for the gas, so it costs nothing. And so is this correct?
No. So as I said, it actually costs like almost anything. We were super diligent in actually putting fees everywhere. So it actually costs things. So when you do process transaction, it actually gonna deduct a fee for converting transaction to the receipt.
Okay. Why then we don't have in the apply method counting for the gas on the moving transaction into the receipt? So in processing of the receipts, we have that if we exceeded the amount, then we need to move the receipts to the delayed receipts.
Yeah. Good point. So the limit for the gas spent on transaction and on everything else is different. So you have a basic 50-50 split of the gas limit separately for converting transactions into receipts and for processing receipts. And this is also something that needs to be revisited because it's a questionable game theoretic solution here. We might want to revisit it later. But because it's two separate thresholds, the code is in different places. All right, I have to jump to a different meeting. Thanks, guys. We're gonna have more videos like this in case you're interested. There's a lot of stuff to go over. And yep, have a good day. Bye-bye.
Thank you. Bye.